So, we'll get 2 candies next time if I can get to Costco and buy the stuff. So I sent all of you the solutions to the midterm exam. I was actually surprised that people had trouble doing simple definite integrals. I don't know, maybe when you were undergraduates you were taught to use Mathematica or MATLAB to do integrals and couldn't do them without help, but there was a computer here you could have used, so I'm puzzled. Anyway, let's pick up where we left off last time, which was basically with an the question?
Yeah, concerning the exam. What percentage of our grade will that be? What percentage will the homework be?
You know, I think what I normally do is if a student does really well on the homework and not so well on the exams, then I weight that student's homework more.
Okay.
And if a student does really well on exams but blows away the homework, then I weight the exams more.
Okay.
So I don't know. Also, I'm not sure what the department's grading policy is at this point. We made a big shift. Later for sure. And so, what is this? Okay, and maybe, so let's see, this is even the wrong chapter. So we were basically starting dispersion relations, and there are 2 things involved in dispersion relations. One is ghost contours. Another one is 1 over x plus or minus I epsilon is the principal part of 1 over x minus a plus I pi delta of x, which is something that we learned about as Cauchy's trick. Let me just display it, probably to make sure that right, minus I pi delta, okay. So there are 3 ideas really in dispersion relations. One is the ghost contour, another one is Cauchy's principal part, and then there's the basic idea that this causal function, so we have E of t is an integral minus infinity plus infinity dt prime of some f hat of t minus t prime, some cause, and this transfers the cause to the effect. But when we say a system's causal, we mean that the effect has to follow the cause, and so this only is an integral. This would be an integral from t prime to infinity. I'm sorry, it would actually be an integral from minus infinity to t of, say, f. So now this is, since t prime is negative, t minus t prime is positive. And equivalently, this function, since it's only, it only is non-zero for positive values of its argument, it can be written as a Fourier Transform, integral 0 to infinity, dt over square root of 2 pi, f hat of t, e to the I zt. Or equivalently, we can write, if we do this integral, then t here is strictly positive, and so for z in the upper half plane, this is a decreasing exponential as you go up, and so this f of z is very well behaved. And in fact, exponentials are infinitely differentiable. In fact, that's your easiest function to integrate or differentiate. If you have e to the x, the derivative of z to the x, the integral of z to the x. And so, apart from a change of variables, you can really do all integrals of e to the x. That's why the fact that some people have trouble integrating e to the minus 2x is sort of worrisome. In any event, f of z is analytic. And we also, though, will assume that f of z, the absolute value of f of z goes to 0 as z goes to infinity in the upper half plane. And so then what we can do is we can write f of, let us say, z0 as 1 over 2 pi I, an integral over a ghost contour, z minus z0, and so z0 is somewhere in the upper half plane. We're integrating along the real axis, and then we add a ghost contour like that. So this is Cauchy's integral formula simply. And we're assuming that this goes to 0 fast enough on this ghost contour, so the contour really is a ghost contour. And then this is in fact just 1 over 2 pi I, integral minus infinity plus infinity, and what did I do? Yeah, you can call it f of x dx over x minus z0. And now once we've done that, we can say, well, we're really only interested in the real axis, so we can bring z0 down, and then we can say this is z0 then is going to be x0 plus I epsilon. So f of x then is going to be 1 over 2 pi I integral minus infinity plus infinity f of, well, this is x0. Or, well, to start out with, it's z0, but I'm letting it be. Let us say x0 plus I epsilon is then f of x dx over x minus x0 minus I epsilon. And now we apply Cauchy's trick to that, and we see that this is the principal part of, this is then 1 over 2 pi I, principal part of the integral minus infinity plus infinity, f of x dx over x minus x0 plus I pi over 2 pi I integral f of x delta of x minus x0 dx. And of course, the delta function, whenever a delta function shows up, it makes your life easier because the integral's something you can do immediately. And so this is 1 over 2 pi I principal parts. Principal part integral minus infinity plus infinity f of x dx over x minus x0. So this is the non-trivial part. This is just 1/2. This is f of x0. So this is 1/2 f of x0. So then you, and here, as we take the limit of epsilon going to 0, this is just f of x0. And so we have f of x0 there, 1/2 that, and so we subtract half of f of x0 from both sides, and what we finally get is f of x0 is 1 over pi I principal part integral minus infinity plus infinity f of x dx over x minus x0. So that's sort of the basic dispersion relation, and then you can do all sorts of things with it. Remember, x is a complex function, and so you can write f is equal to u plus iv, and when you do that, you get you get u of x0 plus iv of x0 is 1 over pi I principal part, and then u of x integral minus infinity plus infinity u of x plus iv of x over x minus x0 dx. And so you can then split that into, you can take the real, remember, anytime you have a complex equation, that's really 2 real equations. And so one of the real equations is u of x0 is 1 over pi principal part of the integral of v of x dx over x minus x0. And then the other one is v of x0 is minus 1 over pi principal part integral u of x dx over x minus x0. So those are called Hilbert transforms, and they're named after a mathematician, Hilbert, who some say stole or tried to get some of the credit for some of what Einstein did. Anyway, I'm not a historian, so I'm not going to take sides in that. By the way, let me just pause for a second. You had a homework question. What was it?
I was just confused on the contour integral of 1 over z squared minus 1.
Yeah.
I wasn't sure what method we were supposed to use to solve that.
All right, I don't remember the problem. What it was.
The contour integral of 1 over z squared
Let's see.
minus
Maybe
1.
I've got here. Let me grab it. So which problem was it?
6.5, I think.
I'm pausing because if one student has a question about something, other students also will. And okay, so we've got an integral dz over z squared minus 1, and you're integrating around a circle z equals 2. And, well, whenever you see z squared minus 1, you should think factor. So you have dz over z minus 1, z plus 1. So this thing has poles here and here, 1, minus 1, but we're integrating over this circle. So you apply Cauchy's integral formula to these two poles. And so or equivalently, you can take this thing and shrink it. And if you shrink wrap it, you get an integral around here plus an integral around there. Or you can say the whole integral is this residue plus that residue plot from the factor of pi I or 2 pi I. So that's basically what you do to work that problem. So getting back to Hilbert transforms and so forth, in physical applications of these dispersion relations, we're integrating here formally from minus infinity to plus infinity, but the variable x in physics problems very often is only sensible for positive values of x. And in that case, you've got to somehow finesse this, the integral over negative values of x. And of course, you can't just ignore negative values of x, you have to find a reason for it. One reason for it might be that f of x is the Fourier transform of some f tilde of k square root of 2 pi. And it may be a Fourier transform of a real function. And if f tilde of k is real, then f of x has special properties, namely f star of x, which would be u of x minus I, v of x, would be equal to f of minus x. Because if you complex conjugate that and f tilde is real, nothing happens here. The only thing that happens is you get a minus sign here. And that means that f star of x is f of minus x, which is u of minus x plus iv of minus x. I'm saying, of course, here that f is u plus iv. Then, if you use, you go back to these Hilbert transforms and you substitute these relations, what you can show, and this is or will be a homework problem, 2 over pi, principal part, 0 to infinity, x v of x dx over x squared minus x0 squared, and then v of x0 is minus 2x0 over pi, principal part, so that's the principal part, integral 0 to infinity u of x dx over x squared minus x0 squared. So the Hilbert relations, Hilbert transform relations look like this, but now you're integrating over physically meaningful values of x rather than the whole real line. So that's something like that is often done. And an example of that is the Kramers-Kronig relations. tell you what, I think what I'm going to do is I'm going to skip Kramers-Kronig until the end of the lecture, and if I have time, I'll do Kramers-Kronig. Or if you want to see it, you can come on Wednesday and ask for it, and I can do it there. So let's skip that and go to phase and group velocities, because I think that's more important and more elementary than Kramers-Kronig. But Kramers-Kronig is directly related to this, so we'll be using these relations for Kramers-Kronig. So for phase and group velocities, this is something that's in typical physics courses. The professor usually assumes that this is obvious and everybody knows about this. And the result is that students can go through college and not quite understand what the phase velocity is, what the group velocity is, and why they are what they are. In any event, we can rewrite this as e to the I k dot x minus omega t, some b of k, d cubed k. And here, b is just h bar cubed times a of h bar k. So b of k is that. So here the idea is that p is equal to h bar k and e is equal to h bar omega, which of course is h nu. So this was Einstein's relation for photons, but it applies to any particle. So now let's just remember what it is that we mean by a phase velocity. A phase velocity is a linear relation x equals v phase times t that keeps the phase constant. And the phase is this or that. And so what we want is that that the phase is constant as a function of time. So in other words, we're going to write 0 is equal to p dot dx minus e dt. So as time goes by, t changes by dt, x changes by dx, and this is p dot v phase minus minus e all that times dt. So the phase velocity is the one such that dx is vp dt, and this thing remains constant, but that means that the phase velocity is basically p over e. Wait a minute, I've got e over p, I've got it backwards. P yeah, e over p, what am I saying? So this is E over P times a unit vector in the P direction. And if we use instead omega and K, then it's a unit vector in the K direction, and it's omega over K. But what you see here is that E is always greater than or equal to P. So this thing, in fact, greater than or equal to Cp. So the phase velocity for a particle of mass m in magnitude, the phase velocity is the square root of m squared c to the 4th plus c squared p squared divided by p. And so that is a factor of c out, and it's the square root of m squared c squared plus p squared over p. And so this is greater than or equal to c. And for a massless particle, that's okay, because it's just equal to c. But for a massive particle, this gives the phase velocity is always greater than 1. And so what you see is that the phase velocity is then the thing that keeps the phase constant, but it's not, it doesn't have anything to do with the actual motion of the particle. So for that, we go to the group velocity. So I should have written phase. If we go to the group velocity, let me just write a line here so there's no confusion. The group velocity, on the other hand, is the thing that keeps the that makes for the, it's where the wave packet's going. And so it's a linear relation, x equals vg times t, that maximizes the amplitude. And that's keeping the phase constant. But notice what the integral is. The integral is over p. So the important thing is that the phase shouldn't vary as you integrate over p. If the phase doesn't vary as you integrate over p, then you get a maximum contribution of a of x and t. And so that means that the gradient with respect to p of this thing should vanish. And that is x minus the gradient with respect to p of e times t. And so the group velocity is the p gradient of e, or equivalently the k gradient of omega. And so for a couple of examples, if we have a non-relativistic particle, mass m, then E is p squared over 2m. The p gradient of E is just p over m, and non-relativistically p is mv. So this is what we associate with the normal velocity of the particle. So that's the group velocity. Relativistically, it's the p gradient of the square root of c squared p squared plus m squared c to the 4th, and that is a little bit different. In fact, it's c squared p over e. And that turns out to be c times pc over e. But you see, e is this, cp is just the square, is just part of the square root. And so this is always less than or equal to c. When m is positive, it's always less than c. So this is what we associate with as the actual physical velocity of the particle. In other words, the quantum mechanical interpretation of the velocity of the particle. Now, actually, the rest of this section is also fairly technical. It's interesting, and let me just give you the description of the physics. people have demonstrated fast light, slow light, and even backwards light. And a description of that is the rest of this section. As I said, it's a little bit technical, so I'm going to skip it, and we'd have to go back to Kramers-Kronig to go through it. But we may have time because it's only 6:03. But the next topic is the method of steepest descent, and I think that's more important. And so let's consider, in the book I used X, and I think that was a mistake of notation because X is confused with is normally the real part of Z, and in this case, X is not related to Z at all. So let's imagine we're integrating in the complex plane dz some function h of z e to the r f of z. So we're replacing x by r. R is just a real number, and in fact, it's a we'll be thinking of r as a positive number. So what's the idea? The idea is that this e to the r f of z is going to be e to the r u of z plus I v of z. And this factor isn't going to influence things too much. It'll mean that there's a phase, but this thing can be doing all the mathematical work. In other words, the integral depends crucially on how r u of z behaves on this path from A to B in the complex plane. And I'm imagining that H and F are both analytic. And analytic in this region. And I'm also going to imagine that U of X, that U here has only, well, first of all, what about U? What we know is that U and V can have saddle points. They can have saddle points, but they can't have maxima or minima. They can't even have relative maxima or minima because they're the real and imaginary parts of an analytic function. F is equal to U plus IV. And we learned when we discussed Cauchy-Riemann equations that the real and imaginary part can only have saddle points. And so what we're going to do is we're going to pick a point where f prime is 0. So that would be, if f weren't analytic, that would be a candidate for a relative maximum or minimum. And we're going to pick a particular point, W. We're going to say there's some point W where f prime is 0. And so we're going to go through W, from A through W to B. And the idea is that if we look around at W, here's W, and then over here is A, over there is B, and so we're going to go like that. So that's the basic idea of the path of integration. And we're going to imagine this in that we're looking at large positive R, and so we really want to we want to stay away from the regions where U is huge. And so we basically follow a trajectory like that. And this will be dominated by the integral near that, and so we're going to choose to go through W in such a way as to make it Gaussian. And so since f prime of W is 0, we can say that near, or Z near W, f of Z is f of W, more or less, plus there aren't any linear terms in Z minus W because the first derivative of f vanishes, so f prime of W is equal to 0. So this then is Z minus W squared f double prime of W. So that's the power series for f of Z. And we're going to say that f double prime of W is rho e to the I phi. And what we're going to do then is choose the contour so that, well, the contour is going to be Z is equal to W plus, I chose Y as the variable, Y e to the I theta. I don't know why I chose Y, but I used X over there. I think if I were redoing this, well, I don't know. Anyway, I think Y is not the greatest choice, actually, because Y, again, suggests the imaginary part of Z, but it's not really the imaginary part of Z. It's just a real variable. So I ought to change that notation. In any event, the key thing is that we want this thing to be a negative, to be basically a decreasing Gaussian. So we want Z minus W squared f double prime of W, which is Y squared rho e to the I phi, that's this term. And then we're going to say that Z minus W is going to be Y squared e to the 2I theta. So this is e to the 2I theta, because Z minus W is Y e to the I theta. So Z minus W squared is Y squared e to the 2I theta. So we want the rho is positive, Y squared is positive. We want this to be minus 1. So that means we need to have 2 theta plus phi is equal to pi. And in that case, we can say that f of Z is approximately f of W minus a half rho Y squared. So now, if we substitute that into this formula here, maybe I should in fact do it here, so let me maybe erase some of this. And so what happens here? What we've got here is an integral dW dz, sorry. dz, and we're going to have h of, well, we're just going to h is not, all the variation and all the mathematical dynamite is in the exponential. And so we're going to approximate this by saying h of z is just h of w.
And then we have e to the r, that's this. Now what's f of z? Well, f of z is f of w, and the rest of that is minus a half rho y squared. And in fact, this dz, well, what's z? We said that z is y, dz is going to be e to the I theta dy. So this is going to be, let me in fact replace that by dy e to the I theta. So now we can pull out the things that are slowly varying, h and f. So we have h of w, e to the r, f of w. And what's left is an integral from minus infinity to plus infinity dy. And that's e to the minus r over 2 rho y squared. And I left out the phasors, so so I have to stick in here e to the I theta, right, just e to the I theta. Now this, of course, is a famous integral, and so altogether then, this is equal to h of w, e to the I theta, e to the x, not x, e to the r, f of w, and the famous integral is square root of 2 pi over r rho. So that's basically the formula for the approximation to this integral that you get from what's called the method of steepest descent. And what you can now do is make contact with these previous expressions. So let me just rewrite this as I of r is equal to, or is approximated as h of w, e to the r, f of w, and now I'm going to move the e to the I theta inside the square root. So I'm going to have 2 pi over r rho e to the minus 2I theta. And now, remember that 2 theta is, or minus 2 theta is equal to phi minus pi, right? Yes. And so this is h of w e to the r f of w square root of 2 pi over r rho e to the phi minus pi. So e to the minus to the right, e to the I phi minus I pi, and so this is h of w e to the r f of w square root of 2 pi over minus r rho, and then we have the e to the I phi. Well, rho e to the I phi is f double prime, and so let me not write rho explicitly. I can just write this as f double prime at w. So that's the final formula then, and this is the general. This is
the steepest descent approximation to that integral. Now here I've assumed there's only one critical point where f prime vanishes. If there are two w's, well then you have to do this thing twice, and then you get a sum over the zeros of the derivative of f. So an example of this is Stirling's formula. So let me show you that. So what we know is that n factorial, of course, is minus 1 to the n dn of y inverse dy to the n. And so that's the same thing as minus 1 to the n, whoops, minus 1 to the n dn dy to the n of the integral 0 to infinity e to the minus yz dz at y equal to 1. And again, this was also at y equal to 1. And we can rewrite this as integral 0 to infinity z to the n e to the minus z dz. And now we can rewrite that as integral 0 to infinity e to the n log z minus z dz. So we want to approximate this by the method of steepest descent. So this f of z here is equal to n log z minus z. So where does the derivative of that vanish? Well, f prime of z is n over z minus 1, so that vanishes for z equal to n. And we're going to set w then equal to n. And so then, applying the method of steepest descent, what we get is that n factorial, which is then approximately an integral. Notice that here we're integrating dz from 0 to infinity, but we're going through this point w, which is z equal to n. And as we go through w, we're approximating that as an integral through w. And so we're effectively going to go from minus infinity to plus infinity through w. That's the fiction that we used in this approximation, that we were going from a to b, but as we got near w, we imagined we were integrating y from minus infinity to plus infinity. So also here, we're going to be integrating minus infinity to plus infinity, e to the n log n minus a half rho y squared dy. And so this part we can pull out. So this is e to the n log n minus n. And then we have the integral minus infinity to plus infinity, e to the minus y squared over 2n dy. Well, this is another famous integral. And so we get that n factorial approximately is the square root of 2 pi n. That's this integral, and then times this. Well, this is this, so just this part is n to the n, e to the minus n, and so that is really n over e to the n. And that's Stirling's approximation I ran about forward. So you see, it's an example of this method of steepest descent. And it may even be the best example of the method of steepest descent. And if you have several saddle points, well then you have to sum over them, as I said. All right, well, we've got about 17 minutes left. And we don't have any blackboard space, but I think I'll use the screen to go through. Let's see if I can sit down on this chair without falling on the floor. Uh-oh. Okay. So this was after dispersion relay. So this is the Kramers-Kronig stuff. And so it starts out with some of the basic equations from electrodynamics, in which one uses complex notation to simplify the mathematics, so you don't have cosines and sines and so forth. So you just, if you want, you can think of that's E of t, but we're only looking at the real part, or we're only looking at the imaginary part. Anyway, Maxwell's equation then is the curl of B is mu j plus epsilon mu E dot, and if you substitute for E and substitute for J equal to sigma E, so you let J equal sigma E, then after a suitable factorization you get this expression, which one can rewrite this way in terms of a complex, the square of a complex index of refraction. And what you can see from this is that at high frequency, this n squared is epsilon mu over epsilon 0 mu 0, and it's apparently true that at high frequencies, epsilon and mu approach epsilon 0 and mu 0, which makes sense actually. And the reason it makes sense is that at high frequencies, you're really looking at very short distances. At very short distances, everything is empty space. You just have charges. So at very short distances, if you're in a solid, you might have a molecule there and a molecule over in the hall, but in here we have vacuum, and so you'd expect that epsilon mu would become epsilon 0 mu 0. Anyhow, so n squared approaches 1 at high frequency, so we can apply the Hilbert transform relations, and then what we get are these expressions. So these are often said to be the Kramers and Kronig relations, but what they actually did wasn't this. What they did was they relied upon something that Lorentz had shown. Namely, Lorentz had shown that the complex index of refraction was related to the complex forward scattering amplitude for light by this equation, where omega is the frequency of the light, and n is the density of scatterers. So these things might be dust particles, they might be molecules, they might be something else, and this is the relation. And you can then infer from this that at high frequency, n approaches 1, and so then what you do is, instead of writing a dispersion relation for n, you write a dispersion relation for the complex n minus 1. And if you do that, then you can imagine there was -1 on this side. But the imaginary part of n minus 1 is just the imaginary part of n. And so the Hilbert transform, which is, let's see if I can get this to, shucks. All right, well, it flipped me all the way back. In other words, we're using these expressions here, and what they give us are these two equations, where at first we, one of those equations gives us this, but there's another relation, namely that the imaginary part of n, well, from the Lorentz expression, the imaginary part of n is related to the imaginary part of the forward scattering amplitude. Now, there's a famous theorem that you learn in quantum mechanics. It's called the Optical Theorem. It's one of the magical relations that sometimes occur in physics when you've got two things that you don't really have any hope of computing or fully understanding, but you're able, from some mathematical principle, such as the unitarity of the S matrix, you're able to say that the total cross-section is related to the imaginary part of the forward scattering amplitude. This is a remarkably general relation, and it's, as I said, it's one of the magical things of physics that you can think of it as a sum rule if you want. Anyway, it's 4 pi c over omega times the imaginary part of the forward scattering amplitude. So now, and then you know that the imaginary part of the forward scattering amplitude is, of course, related to the imaginary part of the index of refraction. And so using those two, you find the imaginary part of the index of refraction is related to the total cross-section in a very simple way. And on the other hand, the Lorentz relation up here tells you the real part of the index of refraction is related to the real part of the forward scattering amplitude. And now, if you put both of these into this expression, which is one of the Hilbert transform expressions, you get this expression here, namely that the real part of the forward scattering amplitude is omega squared over 2 pi squared c times the principal part of the integral from 0 to infinity of the total cross-section divided by omega prime squared minus omega squared d omega prime. And the total cross-section is evaluated at omega prime. So those are the phase and group relations. Now, what I can do is I can sketch this for you in just a few minutes, namely that one can take this complex index of refraction and think of it as a frequency, as a function of the frequency omega, instead of as the function of the wave number k. And then if you differentiate, you get if you differentiate this expression, you get this expression where R means the real part. And so the group velocity then is d omega dk, and that gives you this expression here. And this denominator is then called the group index of refraction. That's what people in the optics world call the group index of refraction. It's the real part of the index of refraction plus omega times the derivative of the real part with respect to omega. And here we're thinking of n as complex. So this n is, as I said, complex.
Now, what is this derivative? Well, it can be, so this is the index of refraction, the group index of refraction. This thing can be big, small, zero, whatever. If it's large and positive, then the group velocity can be slow, and this is slow light. On the other hand, this can be negative, in which case, instead of this thing being big, it can actually be quite small. And that is called fast light. On the other hand, this thing can be so negative that the whole group velocity becomes negative, and that's when you have backwards light. So those are the formulas for that. And I think I'll just let you just sort of think about that, and let me instead turn the lights on and talk about something that I didn't emphasize in the book. In fact, I didn't really talk about it in the book, but perhaps should have. Oh, all right, so let me turn off the line. So what I want is to say something about, suppose we think of a function of two variables. Now, of course, if a function is a function of x and y, I mean, it might be analytic, it might not be analytic. In general, it would not be analytic. And we can, inasmuch as z is x plus iy, and z bar is x minus iy, we can rewrite, of course, x as z plus z bar over 2, and y as z minus z bar over 2i. And in that case, we can rewrite f of x and y as f of z plus z bar over 2, z minus z bar over 2i, or equivalently f of z plus z bar over 2, and this would be I z bar minus I z over 2, just to get the I out of the denominator. And so then, what is, we can think of what is the derivative with respect to x. Well, the derivative with respect to x is the derivative with respect to z plus the derivative with respect to z bar, and the derivative with respect to y is I times the derivative with respect to z minus I, derivative with respect to z bar. And if we're differentiating f with respect to z, say, then what is it? Well, it's the derivative of f with respect to x times 1/2 plus 1 over 2i times the derivative with respect to y. Or equivalently, it's 1/2 partial x minus I partial y times f. And on the other hand, the derivative of f with respect to z bar, well, it's 1/2 the derivative of f with respect to x, and then plus I over 2 the derivative with respect to y. And so, rewriting that, we can say it's 1/2 d by dx plus I d by dy on f. So, that's how we can think of the derivative with respect to z and the derivative with respect to z bar. And it's often convenient, just as the derivative with respect to x and the derivative with respect to y are independent derivatives, so too it's often convenient to identify the derivatives with respect to z and z bar, to think of them this way, and to think of them as independent things. And in particular, you can say, well, what happens if the derivative of f with respect to z bar is equal to 0? Well, that's the statement that the z bar derivative, well, this is 1/2 the x derivative plus I y derivative of f, and f is u plus ib. So what does that give us? That gives us, let me use the economical notation. This is ux plus I dx plus I uy plus I by. All of that is equal to 0. So that's one complex equation, and that's two real equations. And so the real part of that equation, let me get an eraser here to get rid of this. Oh my goodness, that is on very seriously. So what do we say? The real part of this equation is 0 is equal to u sub x minus v sub y, and the imaginary part equal to 0 is v sub x plus u sub y. So what do these equations tell us? They tell us that u of x, u sub x is equal to vy, and vx is equal to minus uy. Well, these, it turns out, are the Cauchy-Riemann equations. So that makes eminent sense. It's telling us that f of x and y, if you do this substitution and, say, do a power series or a Taylor series in two variables of f of x and y, you all the z bar terms cancel, and all you have left are z's. All right, I think that we're out of time. Is there any question, though, before we turn off the video? Okay. All right, so let's... Yeah.